So yesterday we were talking about vectors and scalars. So any measurement you can think of is either going to be vector or scalar. So what were some of the measurements from yesterday that we talked about? We talked about time. Is that vector or scalar? Scalar. We talked about temperature. Scalar. So things that are measurements that are scalar have no direction. They only have magnitude. And what is magnitude? It's how big, how much, how far. It's the size of something. If you add a direction to a magnitude, then you're talking about vectors. So what are some measurements that would be considered vector? So things that have direction, we said force. You know, a force is any push or any pull. There's a whole, we're going to spend weeks talking about forces. So any force or any pull, any push or any pull is a force, and forces have direction. Are you pushing to the left? Are you pushing to the right? Are you pushing north? Are you pushing south? The other vector we talked about was acceleration. Which way is the object accelerating? What other things are vector? So displacement. So let's just jump into this. So displacement and distance. So two terms that are very similar in meaning, very, very similar in meaning. In fact, how many of you guys have heard the term displacement? It's frequently used with fluids. You know, if you have a beaker of water and you put a rock into it, the water is displaced. So this is a similar meaning, but different. What we mean by displacement is displacement is the same thing as distance, but it's distance with a direction. If you take distance and add direction to it, distance plus a direction is what? Displacement. Distance plus a direction is displacement. So distance by itself is scalar. So distance is scalar. Displacement is vector. All right, which of these is going to be more of a pain in the butt to deal with? Displacement. Vectors are trickier to deal with. And the reason why vectors are trickier, you know, for right now, we're just going to put it like this. In the world of vectors, will 5 plus 5 always equal 10? No. In the world of scalar, 5 plus 5 is always 10. Money is scalar. If you have $5 and $5, you put them together, that's $10, right? With displacement, that's not the case. Or with vectors, that's not the case, because vectors have direction. So, you know, for example, if this vector here, you show vectors with arrows. If this vector here is 5, and this vector here is also 5, what are these two vectors going to do? They're going to cancel each other because they point in opposite directions. What if you have two vectors that point in the same direction? So what if you have a vector of 5 to the right and another vector of 5 to the right? What are those going to simplify to? 10, because they agree. They're working together. So vectors are going to make you think more than scalars do. All right, so yesterday we did an example, like if you start, let's say that this dot right here represents your start point. If you go on a journey where you go, let's say 50 miles north, so we'll say, you know, north, south, west, east. So there's our frame of reference. If you go 50 miles north and then you go 100 miles east, and then you come 50 miles south. So here's our journey. What would be the total distance of that journey? 200 miles. So, you know, distance doesn't care which way you're going. Distance is like you take 50 miles, 100 miles, the 50 miles, you add them all up, that's your distance. Okay? What would be your displacement? So look, the symbol that you're going to see for displacement displacement is frequently written as delta x. And the way you read that, delta, what is delta in math? Change, and then x is position. So very frequently you're going to see displacement referred to as change in position. That's another name for displacement. You could call displacement change in position, and it's written as delta x. So for this example here that I just made up, so there's the endpoint, what would be the displacement for the journey? 100 miles east. And the reason that works out, you know, in the vector sense, this 50 miles and that 50 miles, what are they doing? They're canceling. So the displacement that we're left with is this. It's 100 miles directly east. Does that make sense? Another way to say displacement, you know, it's the shortest distance between starting point and ending point. It doesn't care about what happens in between. Displacement is the shortest distance between start point and end point. So the delta x for this example would be 100 miles east. Okay? All right, so let's look at this. So I just want to, let's look at this diagram here, and we're going to look at A to F. So this point right here is point A, and then over here is point F. So we got this car that's going on this very short journey. So this car goes from point A out to point B, and then from point B back to point F. Okay? So what would be the distance for that journey, and what would be the displacement for that journey? From A, so what's the position at point A? 30 meters. What's the position at point F? Negative 50 meters. So those are the positions. So figure out the distance traveled and the displacement. Distance from A, so the car goes from A out to B and then back to point F, which is here at negative 50. So what would be the total distance traveled for that journey? 120 meters. Because the car from A out to B is how far? 20 meters. And then from point B all the way back to there is 100. So the total distance traveled is 120 meters. All right, what would the displacement be? Not just 80, negative 80. So let me show you how to calculate that. So look, anytime you're calculating change, change is always final minus initial. It doesn't matter what it could be change of money, change of time, change in velocity. It doesn't matter what you're doing. It's always final minus initial. So we're going to go position final minus position initial. Oh, and look up here. See that little I right there? That's initial. Another way of showing initial is that little sub-zero. So change is always final minus initial. So where is the final? The car ends up where? Negative 50, right? That's point F. Negative 50 minus, where did the car start? At 30. So this gives a displacement of negative 80, right? Displacement is a vector and it has direction. What is this negative right here telling us? That's the direction. The negative is the direction. What's the 80? The magnitude, the distance, right? Vectors always have magnitude and direction. Now, what does negative mean? What is that telling us? So the sign convention here, to the right is plus, to the left is minus. Isn't that what you guys do in math class? In math class, you guys go like this. Plus, minus, plus, minus. These are our directions. You know, so if you're dealing with a horizontal situation, negative means to the left, positive means to the right. So plus and minus in physics tells us the direction. Easy enough? Okay, one more thing and then we're done. Okay, velocity and speed. Velocity, so these are two terms that you've heard before. Raise your hand if you've heard of velocity. Raise your hand if you've heard of speed. They're pretty much the same term, but one is vector and the other one is scalar. Velocity is vector, speed is scalar. Now notice, what is velocity using in its definition here? What is delta x? Displacement, which is also a vector. What is speed using in its definition? Distance, which is a scalar. Okay? Which one of these is going to be more of a pain in the butt? Velocity, because, you know, it's a vector and direction matters. So for example, let's look at A to F again, and then we're done. And let's just say that A to F, I'm going to give you a time. Let's say the time from A to F is 10 seconds. I want you to calculate the average velocity. Oh, and see that little line above the V? That indicates average. The average velocity between A and F, and then I want you to calculate the average speed between A and F. All right, for finding, let's do speed first. So speed is distance over time. What's the distance traveled from point A out to B all the way back here to point F? It was what? 120 meters. And then I told you the time. Let's say that that takes 10 seconds. So what would be the average speed for that journey? 12 meters per second. Now, and that's what we use in everyday life. In everyday life, you would talk about speed. Now, average velocity. What was the displacement? So velocity is displacement over time. What was the displacement between A, which is right here, A, and F, which is over there? The displacement was what? Negative 80 over 10 seconds. So this gives us an average velocity of negative 8 meters per second. Why negative? Negative means to the left. To the left. So notice that for the same exact journey, velocity and speed are not the same. Does that make sense? Oh, and one thing I didn't mention here are the units. What do we measure displacement in? Meters. What do we measure time in? Seconds. So velocity or speed is going to be given in meters per second. What do we use in everyday life? We don't use meters per second. We use what? Miles per hour. It does the exact same thing. Miles per hour and meters per second, they do the same job. Meters per second is the choice physics unit though. Okay?